Hello everyone and welcome to lesson 7.4 on operations with rational expressions. I'm actually going to split this video into three parts. Part one is going to be this video, multiplication and division, as you can see right there. Part two will be how to add and subtract. That involves getting a common denominator. And then part three is going to be on what's called a complex fraction. Check out the corresponding videos for what you need. And I guess let's just get started, yeah? So we're starting Unit 7B. This is the second half. And the title, as suggested, it says Operations with Rational Expressions. We say rational expression, we're just talking about a ratio or fraction, right? So, multiplication, division of fractions. For example, if you had 2/3 and you need to multiply this by 3/7, right? Well, you just multiply across. 2 times 3 is 6. 3 times 7 is 21. And both of these numbers are divisible by 3, so you can simplify the fraction as 2/7. You may also, and I would hope you would know this, or notice this, but when you multiply 2/3 times 3/7, you could notice that the factor of 3 is already on top and bottom, meaning they cancel out to 1 because 3 divided by 3 is 1. So I actually don't need to do 6/21, right? Because I can actually just take it from here and get to 2/7, seeing that the 3 is on top and bottom, cancel it out, yeah? Now, when you do division of fractions, we have this little saying, this little acronym. No, it's not an acronym. It's just a mnemonic device. A little saying. You say, if you had A over B, it's this rule right here, divided by C over D, you can solve this or simplify it by doing what's called keep, change, flip, right? So you're going to keep the first fraction, A over B, and then change the division symbol to multiplication, and then flip the other fraction like so, like it's D over C. So, for example, if you had a half divided by 2/3, then that would be equal to a half times 3/2. And now that it's multiplication, you do 1 times 3 in the top is 3, 2 times 2 in the bottom is 4. And that's it, yeah? So honestly, if you understand those two ideas, that's all this video really is. But there's a few other things we're going to talk about. Factoring, and we're going to talk about restrictions on our variables, okay? So I'm going to move to example 1 here, okay? And the goal is to simplify this as much as possible. So we want to multiply these, but when you're multiplying them, you also want to cancel out what's called common factors, right? Kind of like that example we started with. What was it? It was like a half times 2/7 or something like that, right? Where the 2's canceled out. I think it was like 2/3 times 2/7 or something. I don't know. Anyway, we're going to start example 1 by factoring everything. And so we say there's a numerator, there's a denominator. I'm going to factor all of it completely. Yeah. So on number 1, in the numerator, the first fraction is right here, 10x squared minus 5x. I notice a GCF, greatest common factor, of 5x. I'm going to factor that out. And what's left behind is 2x minus 1. That's it. Done. Beautiful. Okay. I'll move to the denominator now. This is 2x squared plus 3x minus 2. This is a trinomial, so you could do a little x puzzle. 2 times -2, right? That's -4, and then a 3 here. And you can solve the x puzzle. You can say 4 and -1, make that work. And keep in mind, a lot of students are still making the mistake of saying that this is x plus 4 and x minus 1. Be careful with that, yeah? When the coefficient is not 1, for example, it's 2 here, you need to use either grouping or kickback method. I'm going to do kickback method in this video just because it's quicker, and we've already talked about factoring techniques, and I don't want to spend too much time really doing the factoring. I just want you to see the process because I know you guys can factor. You don't need to see me do all of that all over again, right? So anyway, I would say this is x plus 4 over 2 times x minus 1 over 2. 4 over 2 simplifies, but 1/2 doesn't, so the 2 comes out back in front, right? And it's just a quick aside, a quick review. I'm getting this from this 4 and this -1 and dividing those by the lead coefficient 2. Now, that means my denominator factors as x plus 2 and 2x minus 1. And then I'm going to do the other. X squared minus 4, that's a difference of squares, which factors as x plus 2, x minus 2, all over. And then I have 10x squared. Now, 10x squared, we wouldn't typically really factor that. You could factor out what 10 is and stuff like that. You are perfectly okay to leave that as 10x squared. Although, I'm going to write this slightly different just to point out something. 10 is 5 times 2, and x squared, well, that's 2x's multiplied, right? And I'm doing this for a reason, and that is because if I look at the numerator and the denominator, right, the thing is you're multiplying, you're taking this fraction times this fraction. And when you do this kind of multiplication, you just multiply the tops together and you multiply the bottoms together. So, this, and then I'm just going to say, hey, this is actually all over one fraction. That's 5, and that's 2, and that's x, and that's x, right? And so now it's all just multiplied. These are multiplication symbols. Everything's connected here. And now that it's all one giant fraction, I just look for common factors on top and bottom. 2x minus 1 and 2x minus 1 cancel. 5 and this 5 cancel. That's why I broke the 10 up into 5 times 2 to see that the 5s cancel. This x cancels with one of those x's, and this x plus 2 cancels with this x plus 2. And if I'm just looking at what's left over, what's remaining, I've got x minus 2 in the numerator, and looks like a 2x in the denominator. And that is it. And so I box this and I say, ta-da, I'm done. And so that is multiplying. So it's really just multiply across, but you had to factor to begin with and then look for common factors. Now, I did mention something about restrictions on your variables. So yeah, we're doing fractions. And when you're doing fractions with variables, well, variables could be anything. Thing is, there's one number you don't want to divide by. Can you think? That number is 0. You say we don't want to divide by 0. So when you're doing this, it's important at every algebra step to look at the denominator and think, is there an x value that could cause division by 0? So I'm actually going to erase all these little blue streaks I did right here to really look at the denominator just one more time. Yeah. So after I've simplified everything, I'm going to say, okay, sure, it's equal to x minus 2 over 2x, but what should x not be, right? What are values that I would not want to plug these in because technically they cause division by 0, right? If it was just this expression all by himself, there'd only be one thing, and that'd be 0. But this came from a product of these two rational expressions. So what causes division by 0? Well, it's the roots of every factor in the denominator. You see x plus 2, what would make this 0? Well, -2. So I'd say x can't be -2. That would cause division by 0. 2x minus 1, set that equal to 0. You get 2x equals 1, then x equals a half. Yeah? So don't be a half. And then lastly, this one always gets students. You have an x here. You also have an x here. That's basically the same thing. What would cause x equal to 0? 0. So I would say 0 can also not be one of the expressions or one of the values of x. I wouldn't want to plug that in because it would cause division by 0. This variable restriction, it's just good practice, okay? When you get into pre-cal, get into calculus, it's important to think about what values can my domain take on, right? What am I allowed to put into a function? And so this gets you in the habit of just recognizing what is the domain of the function? What are you allowed to put into this, right? And if you remember from 7a, unit 7a, whatever makes the denominator 0 causes vertical asymptotes and holes. That's basically what you're identifying, is what x values cause those things. Don't put those in. Okay, let's go to example 2, and it's just more of the same thing, but it's to model the keep, change, flip idea, right? So we're going to start by factoring. X minus 2 is already not factorable, it's just x minus 2. In the denominator, I have x squared plus 12x plus 35. That's 35 and 12. What two numbers make this work? That'd be 7 and 5. So this is going to factor as x plus 7 and x plus 5. Done with that, right? And then I'm going to factor the numerator up here. So this guy, this is negative 10 and 3. And what's going to make that work is 5 and negative 2. So this will factor as x plus 5 and x minus 2. The other one on the denominator, this 3x plus 21, has a GCF of 3 factored out. The other factor is x plus 7. Now, and so I'd say, look, this divided by is x plus 5 on top, x minus 2 over 3 times x plus 7. But the rule when doing division of fractions is to keep, change, flip. At least this is a way to think about it, right? So I'm going to keep the first rational expression as so. I just copied that down. Change the division to multiplication, and then flip the other fraction like this. X plus 5 and x minus 2. And now that everything is all together like this, I'm going to put parentheses around this. I'll look for common factors on top and bottom. I'll notice an x minus 2 here and here, and an x plus 7 here and here. No other common factors, so the numerator is only 3. And you'll notice that you have this x plus 5 and this x plus 5. Well, that's 2 of them, right? So that's the factor x plus 5 repeated twice, right? It's occurring twice, so it's an exponent of 2. And thus, my answer. Now, we should talk about the domain restrictions, right? The variable restrictions on x. So I'm going to erase those again. Remember, we don't want to divide by 0. Now, this one's a little tricky because there's multiple points in our algebra where we are maybe possibly dividing by 0, yeah? The first is just on step 1, right here, the denominators that we factored. So what makes x plus 7 0? Negative 7. What makes x plus 5 0? Negative 5. Go to the other denominator. What makes x plus 7 0? Negative 7, right? So I know that x should not be negative 7 or negative 5. But, when I flip it, right, this division symbol flips this equation, and now I have an expression where x plus 5 and x minus 2 are in the bottom. So they kind of switched. And if I look at that, x could not be negative 5, and x could not be 2. Well, I already have the negative 5 right there, but I don't have a 2 written, so I'm going to put that there as well. And so this is just a note that if I were to plug numbers into this expression or into these expressions, I'd want to be careful and observe what's happening around negative 7, negative 5, and positive 2, because they are probably going to cause division by 0, and I don't really want that. Yeah. I do think if I go to Desmos, it should let me do it. You know what? I'll take the time. I'll take the time real quick. If you don't want to see this, go ahead, scroll. You can see some more examples, okay? Let's see here. I had x minus 2 over, I'm just trying to model something for you, x squared plus 12x plus 35. And I'm going to let this be f of x. F of x is this. And I'm going to take g of x. And what was the other function? X squared plus 3x minus 10 and 3x plus 21. It was x squared minus 3x plus 10. No. Plus 3x plus minus 10. And it was, I already forgot, 3x plus 21. Okay, 3x plus 21. 3x plus 21. Okay, so I have these two functions. I'm going to get rid of those. And I'm going to look at the ratio f of x divided by g of x. See, so Desmos will do this. The thing is I said x should not be, we'll go back, x should not be -7, -5, or 2. So if I go to Desmos, -5 you can clearly see, oops, x, hello? X equals, it's not typing, here we go. X Whoa, stop it. X equals -5. There we go. This is a vertical asymptote, which obviously we're not touching. So the expression really isn't defined there, right? It's undefined at -5. The other two things I had were -7 and 2. Now I wonder if Desmos will show me this. So here's the -6. Let's go, whoop. Oh, there it is, right? Whoop, can you see it? -7, comma, undefined. It doesn't exist here. Now, I wonder if it'll do it for 2. Let's see. There's a chance it may not. Hey, there it is, right? Boom. So at 2, it's undefined as well. So you can see that when I took the ratio of these functions, there was a hole at -7 and at 2, and then there was a vertical asymptote at -5, meaning I would want to be careful with those values because the function's actually not defined there. Yeah? Okay. And so that models why maybe putting those restrictions is a little important. Yeah? Okay. Well, as far as part 1 goes, that's pretty much it. You can go ahead and proceed to part 2 if you'd like. I am going to extend this video and do the next 4 problems just as additional practice. You know, if you really... You know, you're a completionist and you want to make sure you have all the notes filled out. You want to keep watching. Absolutely go ahead. But this is enough information that you've got the idea. Yeah? Okay. So go have fun in the next lesson or stick with me and we're going to walk through the rest of these. Okay? So this is now student practice. And honestly, I'm just going to kind of do it quick. Yeah? I'm going to factor quick. You can pause to think about the numbers if you'd like. Going to multiply these two expressions together. I'm going to start with the numerator on the first fraction with a GCF of 4x, yielding x minus 1 here. In the denominator, you see 2x squared plus 4x minus 6. I will caution you about kickback method on this because it has a GCF. So this guy is actually 2 times x squared plus 2x minus 3. If you were to do the kickback method on this, it's always finicky with GCF because then both things divide and then there's nothing to kick back, but there's still a coefficient, yada, 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 whatever. To pull out the 2 first, do the x puzzle, -3 and 2, gets you 3 and -1. And so this factors as x plus 3 and x minus 1. Times, let's factor the numerator here. 2 numbers multiplying at -6 would be positive 3 and -2. Since that adds 3 minus 2 is 1x, right? And then in the denominator, 4x squared plus 8x, that has a GCF of 4x. Pulling out, you have a factor of x plus 2. So what cancels? X minus 1, x minus 1, x plus 3, x plus 3, x and x, 4 and 4, right? So all of that kind of cancels. Was I missing anything? Oh, there was a 2 down here. There was a 2. I thought there was something missing. Remember, from this guy right there, there's a 2 right there. Okay, cool. So everything is canceled. I get x minus 2 on top and 2 times x plus 2 on bottom. And thus, my result. The domain restriction. What makes the denominator 0? X plus 3, you don't want to be negative 3. X minus 1, you don't want to be 1. 4x, and it's actually not the 4. You don't really care about whether it's a 4 or not. It could be 5x, it could be 10x, whatever. The fact that it's just x, if x is 0, then you're dividing by 0. So don't be 0. And then the other factor, x plus 2, the root of that is negative 2. So there are your domain restrictions for that first one right there. Okay? All right, move to number 2. We're going to do the same thing. I'm going to start with GCF on the denominator. This is 10 over 4. Factors out, I get x minus 2 here. Now, I'm going to go ahead and factor this guy with a GCF of 2x, leaving me x plus 3. And I'm going to factor this x puzzle. 2 numbers multiplied get negative 6 would be plus 3 minus 2. Okay? Didn't we have that one earlier? Yeah, we did. It was actually in the last one. Now, I'm doing keep, change, flip, though. This is division. I'm going to change this to multiplication and flip this fraction. So this one's going to be on top, the x plus 3 minus x minus 2, and this one's going to be on bottom. So I'm going to change that to multiplication, and on top is x plus 3, x minus 2. On bottom is 2x times x plus 3. Now, the x plus 3's cancel, the x minus 2's cancel. And you may notice that, if you got a 4 and a 2x here, the 10 on top, the 10 is a 5 times 2. That means this 2 can cancel out with that 2, leaving you with 5 on top and 4x on bottom. Done. As for variable restrictions, it's what makes the denominator 0, but it's kind of at all steps. So in this first denominator here, 4x minus 8, so x minus 2, you don't want x equal to 2. But look at the other denominator right here, whose factored is right there. You don't want to be negative 3, and you don't want to be positive 2. So we already have the 2, but we don't want to be negative 3. Then it gets flipped. This denominator is the same, but then you have to look at this. You don't want to be negative 3, which we already have, but then this x, you don't want to be 0. So we put those restrictions on. Not 2, not negative 3, not 0. Nice. Okay, we move to number 3. I think this is just more of the same. Some more GCF factoring. Starting with the numerator, you get a 2x squared that you factor out. You get an x minus 6 on top. On bottom, another trinomial with negative 12 and negative 4. The numbers that'll make that work are x minus 6 and x plus 2. This numerator, you're going to factor out 8x squared and then get x minus 3, because 8 and 24, right? And then this one, positive 15, so you need a double negative here for the negative 8. You need x minus 5 and x minus 3. Keep in mind that these are going to switch, right? So this is top, this is bottom now, times the denominator is x minus 5. No. That's what we just said. We're going to switch it. The bottom is 8x squared, x minus 3, and the top is x minus 5, x minus 3. Because, again, I'm doing division. Division is keep, change, flip. KCF, almost like KFC. But not. But it's not KFC. Okay. So, what cancels? Well, the x minus 6's cancel. The x minus 3's cancel. This x squared and this x squared cancel. And this 8 is 4 times 2. So get rid of the 8. And then that 2 and this 2 cancel. This leaves us with x minus 5 on top and 4 times x plus 2 in the bottom because of this 4 and that x plus 2. Okay? Ta-da! And that's our fully simplified expression. Again, state the variable restrictions. What can x not be? Well, the denominator here would say 6. Here, it would say -2. Here, it would say 0. Here, it would say 3. And don't forget the original expression, this denominator, which would have 3 and 5. So, what can x not be? It can't be 5. It can't be 3. It can't be 0. It can't be -2. It can't be 6. A lot of restrictions on x there, yeah? Because there's a lot of possible, there's a lot of factors canceling out, a lot of factors in the denominator. Okay? All right, last one for the video is number 4, which is probably the one you might be interested in seeing, because this one's a little different from those 3. For one, it's not only in terms of x, it's multivariable. And 2, because of that, the factoring is a little different, right? Well, I mean, it's the same thing, but it might be a little harder. And the domain restriction, or variable restriction, there's something about this one that's going to be a little like, what do I say here? What do I do? So we're going to start off. Most of the factoring is not too bad. With the numerator, we're going to go with a GCF of 4y and get y plus 1 here. In the denominator, you get the 6, you get the 2, so you know you can pull out a 2. You also have a y and a y squared, so we're going to pull out 2y. What'll be left behind is 3y minus, 3x, there's an x, minus y, and that's what's left, okay? Okay, then times, I'm going to come over here, y squared minus 1 on the denominator, that's a difference of squares, right? That's a squared minus b squared. So this factors as y plus 1, y minus 1. Now, the one that's tricky, the one that gets people in class, is this numerator. You say, how do I do that, right? Is it a trinomial? I mean, it is. Do I do 9x squared y squared over -6xy? And I would say, why, yes, you do. That is what you do. But how do you write this, right? Like, how do you actually factor such a thing? And the thing is this one's kind of difficult using an X puzzle. I wouldn't actually recommend an X puzzle. It actually follows a factoring pattern we're familiar with. Here's an example. 9x squared minus 6x plus 1. This should be ringing a bell, thinking, wait a minute, that looks familiar. That's like 3x squared minus 2 times 3x plus 1 squared. That's what's called a perfect square trinomial, which factors as 3x minus 1 squared. The thing is there's a y here. So the 1 is like a y, and then this one is like a y. So then this one is like a y and a y, which means that's a y. So this is a perfect square trinomial which factors as 3x minus y squared. Okay? Now, what cancels? 4 is 2 times 2, so this 2 cancels with that 2. This y cancels with this y. This y plus 1 cancels with this. And then right here, that's 3x minus y squared. Or in other words, you could write that as 3x minus, that's 2 of them multiplied. So one of them cancels there. And so what are we left with? We're left with this 2, this 3x minus y, and this y minus 1. So I've got 2 times 3x minus y over y minus 1. That's the final expression right there. Now, what's tricky about this is the variable restrictions, right? Now, there was no crazy division, so I don't have to do all that. I can really just look at the denominator, and the first few are easy. 2y. Well, what makes y 0? 0. So don't plug in 0. Y plus 1, the root of that is -1. Y minus 1, the root of that is 1. And those are relatively straightforward. Most students see those. The one that's tricky is this. 3x minus y, right? What do you make of that? Well, you shouldn't divide by 0. So whatever 3x minus y is, it shouldn't be 0. The thing is, if I add y to the other side of this, I don't even know what to call it. I want to call it an inequality because it's an unequal. It's not equal. I suppose it classifies as 1. Then I would get 3x is not equal to y. Or in other words, y is not equal to 3x. So I don't know what x is, but I do know that whatever I'm using for x, I don't want to use a y that's 3 times as much. So in those variable restrictions, y would also not equal 3x. And that was the trick to that one. A little tricky, huh? A little tricky. Again, these variable restrictions, it's not you'll definitely be tested on your ability to do these operations, but the restrictions themselves, that's not a huge test item. You will see it on the homework for good practice, but it's something to keep in mind when you're doing your algebra. It's to just kind of build good habit and thinking, if I were to get an answer, if I were to solve an equation or something and get an x that was one of these, would that actually work out? Would that actually make sense with the equation I started with, right? So that's kind of why we do that. Okay, well, that wraps up lesson 7.4, part 1, multiplying and dividing. If you watched all the way through, keep on going. We got addition, subtraction next. Thanks for watching, and I'll see you in the next one.